today let's continue with the topic of rotation. Now we will see in this chapter some new concepts such as the inertia, moment of inertia, rotational inertia, and also the rotational kinetic energy of a rotating object. But before going on to the inertia, let's solve an example from the previous part to just make a short review. Let's say we have a disk that starts to rotate from rest, so initial speed is 0, at time 0. So we start our chronometer at any time we like, as already said. So we start the time at time 0, and then the disk starts to turn. At the beginning it has some acceleration, so it will get faster and faster. So it reaches the angular velocity of 180 RPM. RPM means revolutions per minute, as we have said before. At time 10 seconds from the beginning. Then it continues to turn at this velocity for 10, t and 15 seconds. At time 15 seconds, the power is turned off. So it starts to slow down, decelerate. It starts to slow down and comes to rest, stops at time 45 seconds from the beginning. So we will now find the following quantities. Find the accelerations for the first part and the last part. Find the angular accelerations for 0, t and 10 for the first part in the accelerating part, and between 15 and 45. So the first part is to find the acceleration. Second thing is find the total angle swept. Total angle theta swept, and see the total number of revolutions, n. Find the total number n of revolutions during the whole period for 0, t and 45 seconds, and let's add this last part. Find the average angular speed omega bar. Find the average angular velocity omega bar. Let's say just these parts. So as we see from the problem, there are three parts. Let's first try to show it schematically before starting to solve the problem, because it is important in physics not just to start solving a problem immediately by just making some calculations, multiplications, additions, etc. Before you do any calculation, please try to think about the problem and the way you will follow, you choose to follow. So in this part, in this problem, as you see, there are three parts. So first of all, along a time axis, for instance, along a time axis, let's say this is the time axis in terms of seconds. So this is the beginning, 0. What does the disk do at 0? It starts to rotate from rest. So we know that there is no initial speed. But the important moments are 10th, 15th and 45th seconds. So let's say 10, 15 and 45. These are the critical moments in this problem. In the first part, let me separate these. Let me call them 1, 2 and 3. First part is accelerating part, second part is constant speed, because it continues to turn at this velocity. At this velocity means whatever velocity it has at the 10th second, it goes on at the same speed for these 5 seconds, and then since the power is turned off at 15, in the last 30 seconds it just decelerates. So there are 3 different regions. There is no constant single acceleration. There are different accelerations. In the first part, third part, but in the middle part, as you see, there is no acceleration, no angular acceleration either. So let's find the necessary thing, which is the velocity here. So at this velocity, at this moment, what is the velocity omega? First, we have to find that one. Is it given? Yes, it is given, but in a different unit. It says 180 revolutions per minute. So revolution per minute is not an SI unit, so we should convert it to radians per second. Therefore, let me first group the 3 parts. First part is accelerating part. So there is a certain alpha which is positive. Second part is constant speed, so alpha is 0. We understand from the problem. And the third part is simply decelerating part. Therefore, alpha is negative. And this omega is given indeed, but it is given, as I said, in a different unit, RPM, revolutions per minute. So we should convert it to radians per second. We should convert hundred and 80 revolutions per minute to radians per second. And we have seen before in the previous lecture, we have seen how to convert RPM, revolutions per minute, to radians per second. 180 should be multiplied by 2 pi so that it becomes not revolutions but radians per minute. But we should also divide it by 60 to convert minute to seconds. Therefore, there is some cancellation. Let's say this is 3. So that omega is now taken as 6 pi. Now it is radians per second. We should use omega to find the acceleration in the first part. What is the definition of an angular acceleration? Change in the angular speed divided by the change in time. What is the change? It starts from 0 to reaches 6 pi. So it is 6 pi minus 0, and it takes 10 seconds for this increase to occur. So we have to divide by 10. Hence we get alpha, let me call it alpha 1, angular acceleration in the first part. It is just 0.6 pi. You can leave your result as 0.6 pi radians per second squared. Remember that the SI unit for angular acceleration is radians per second squared. Of course, in the second part, alpha 2 is just a 0 because there is no change in the speed. And what about alpha 3? In the last part, in this part, we have alpha positive. In this part, we have no alpha, 0. But between 15 and 45 seconds, there is a drop in the speed. So in this part, we have an alpha which is negative, as we said here. And it is again found by the same expression. What is that expression? Alpha 3 is final speed minus initial divided by the time it takes. What is the final speed? 0, because it stops at the end of 45th second. 0 minus, what is the speed just here? Since it doesn't change the velocity in this 5-second interval, it is still 6 pi. 6 pi. 0 minus 6 pi divided by, what is that difference? 45 minus 15. So it is 6 over 30. 0.2. Therefore, alpha 3 is just negative because it is slowing, the disk is slowing down. So negative 0.2. 0.2 pi. You don't multiply, you have to multiply by pi or take it as 3. So you can leave your result as 0.2 pi radians per second squared. If the problem tells you that you can take pi as, for instance, 3, then you just multiply and get the numerical value. Of course, if you compare the acceleration in the first part and the last part, this is, as you see, 1/3 of the first, 0.6, 0.2, 1/3. So we understand that alpha 3 is 1/3 of alpha 1. And it is obviously seen that that change between 0 and 6 pi takes a time of 10 seconds in the first part. However, it takes 3 times 10, 30 seconds in the last part. So obviously this acceleration has to be 1/3 of the initial acceleration, and also it should have a negative sign because it is now slowing down. The object is decelerating. And also in the middle part, where there is no change, alpha is just 0. So we solved the first part, found the accelerations. Now the second part says find the total angle theta swept. There are different ways of finding the angle swept. Now let us use more than one way to find them. For example, we can use the following equations. We are now in part B, and we want to find the angle theta. Which equations do we know for finding such kinematical parameters? Let me write them again on the board and see which one we can use. For instance, omega is equal to omega 0 plus alpha t. Theta is equal to initial velocity, final velocity, omega of course, the angular velocity, divided by 2 times the time it takes. Or theta is initial velocity and time plus 1/2 acceleration and t squared, and finally final angular speed squared is initial 1 omega 0 squared plus 2 alpha theta. As you see in the first one there is no theta dependence, so first one cannot be used for this purpose. Second, third, fourth can be used. Let's use all of them and see which one is more, for example, practical in such cases. Let's use number 2, for instance. Can we use it? Yes. To find theta total, we should find all three parts. To find theta total, we should get theta 1, theta 2, and theta 3. So theta total is the sum of these three parts. As we have seen, there are three parts: accelerating, constant speed, decelerating. So theta 1, for instance. Let us use this equation if we can. Yes, we can. Because we know the initial speed and final speed for the first 10-second interval, which is 0 plus 6 pi, remember the velocity was 6 pi, 0 plus 6 pi divided by 2 times, what is that interval? It is 10 seconds, so multiply by 10. 5, so 30 pi. So that theta 1 is 30 pi radians. Now, this theta 1 could be found by the other equation as well. Or, we are still in the first interval, between 0 and 10. Or, this theta 1 can be found by the second equation. Initial speed omega 0, which is 0. So it is just 0 times 10 plus 1/2 alpha. What is alpha? 0.6 pi. 0.6 pi multiplied by the time squared. What is that time? 10 squared. So it is 100. 100 over 2 is 50. 50 times 0.6 is 30 pi again. So theta 2 is again 30 pi radians. So of course we should get the same result. Otherwise it means we made a mistake. Or still we can apply the last equation, or omega squared. Do we have omega? Yes. 6 pi. Omega squared equals initial speed omega 0, which is 0, plus 2 times alpha. What is alpha? 0.6 pi. And the unknown theta. Theta 2. Theta 1. We still talk about theta 1. Alright. Now there's a cancellation. That theta 1 is 6 pi times another 6 pi squared divided by 0.6 pi and a 2. So one of the pi's will cancel. This will be 10, 6 over 0.6 is 10. It is 60. 60 by 2 is 30. So obviously we find again theta 1 is equal to 30 pi. So of course, by all these three ways, we obtain the same result as expected. 30 pi. So this is just the angle swept in the first 10-second interval. Now, theta 2. How do you find it? It is the angular distance. It is the angle. Rotational distance is the angle, as you have seen. So theta 2 just between 10 and 15 seconds. 10 and 15 seconds. So theta 2, of course again we can use all three, but since there is no alpha in this middle part, For example, you can easily take this one, omega 0, omega are the same. In this case, omega is not 0, because now we are talking about, let me draw the time axis again. So this part, that part was, remember, theta 1, this part was theta 2, and the last one is theta 3. So we obtain the first one by three means. Theta 2 is simply, theta 2 is just omega 0, which is 6 pi. Final speed is again omega, which is 6 pi, times the time interval. What is that time interval? It is between 15 and 10, not from the beginning. So this is 5 seconds, 6 pi. Theta 2 is also 30 pi radius. By coincidence, it is also 30 pi. And last, of course, we can obtain the same result by other means. For example, if you use the third equation, in this case, omega 0 times t, 6 pi times 5, plus nothing because alpha is 0. Again here, omega squared, omega 0 squared, here we cannot use it because anyway, alpha is 0 here. So the fourth one cannot be used for this purpose. But second and third, you, of course, give the same result. Theta 2 is also 30 pi. Now theta 3. In the last part, again we can apply one of these equations. For instance, if you apply this one, final speed, initial speed is 6 pi plus 0, because it starts with 6 pi and ends up with 0 at the end, it stops. So divided by 2, and what is the time interval? It is the difference between 45 and 30. So it is 45 and 15. So it is, so this is a 30-second interval, 30, 90 pi. So that theta 3 is 90 pi radians. Can we get the same result by other equations? Of course. Let's use the third one, or let's use the third equation for finding theta 3. Initial speed. Now, of course, it is an initial speed. Omega 0 is not 0 now, because we are interested in the last interval. Its initial speed here is omega equals 6 pi, and final speed is 0. So initial speed in this interval is 6 pi radians per second. So it is initial value 6 pi multiplied by how many seconds? 45 minus 15 plus 1/2 alpha t squared. But alpha is a negative value, so it is, as we remember, minus 0.2. So we have a subtraction here, 1/2 0.2 pi for alpha. T squared is this time but squared, 45 minus 15 squared. So this will give us 30 times 6, it is 180 pi, minus, this will be 0.1 pi, but this will be 30 squared, 900. 1/10 of that, 90 pi. So the result will be 180 minus 90 is again 90. So this is also 90 pi radians. Please remember also that, make sure that theta should be a positive number, because it is just turning, getting faster from the beginning, turning at the same speed for 5 seconds, then slowing down. But it never turns back during this 45-second whole motion. So if you, by mistake, if you get a theta negative, it means you made a mistake, because at the end it stops. It doesn't start to turn back. So totally, of course this theta 3 can be found from the last one as well. Last one. Final speed is 0, initial one is 6 pi squared. 6 pi squared divided by 2 times 0.2 pi gives us again the same result. Let's also check it. Or omega squared, final speed is 0. Initial value is 6 pi squared, 0, now 6 pi squared, 2 alpha pi. What is 2 times alpha? It is 2 times 0.2 pi and unknown theta. So that theta 3. This theta 3 turns out to be 6 pi, another 6 pi divided by 0.4 and pi. 0.4 and pi. So one of the pi's will cancel. 36 over 0.4 will be again 90 pi. So that theta 3 is also obtained as 90 pi radians. Now totally we will find the total angle swept. Totally, theta t is, as we have said, theta 1 plus theta 2 plus theta 3. So from the beginning we know that it is 30 pi, 90 pi. So totally 150 pi. Radians. And in part C it says find the total number of turns. In order to convert the angle swept to number of turns, of course we have said that we have to divide by 2 pi because one full turn corresponds to 2 pi radians. If 2 pi corresponds to 1 turn, how many turns correspond to 150 pi? So that n is equal to angle swept divided by 2 pi in any case. So it makes 75 revolutions. 150 pi divided by 2 pi, so n turns out to be 75 revolutions or 75 turns. At different rates, but totally from the beginning until the 45th second, it makes totally 75 full revolutions. And part B says, find the average speed. How do you get average speed? It is theta total divided by total time. Theta total is, go back to the angle, 150 divided by 45 minus 0 from the beginning. So totally 150 by 45, 150 pi by this. If you take, for instance, now pi as 3, for example, if theta is approximately 3, then 450 by 45 is almost 10 radians per. So omega bar is, sorry. Now in this part of the lecture, let's talk about another important thing, which is the rotational inertia or moment of inertia. As we have said in the previous lecture, everything in kinematics, linear motion, has a corresponding counterpart in angular rotation, rotational motion, angular motion. For example, we said that x in the linear case corresponds to angle theta in the angular rotation. Or initial speed omega 0 is corresponding to initial speed v0 is corresponding to omega 0 in the initial case. V final speed corresponds to omega. Time, of course, is again time, but acceleration, linear acceleration corresponds to angular acceleration alpha. And linear distance was x, time and time. So these are the first basic things, and their counterparts in the angular motion. But also, we have seen Newton's laws in the previous chapters. Before we deal with angular motion, we have seen Newton's laws. So force was equal to mass times acceleration. We will see the counterpart of force later. It will be torque as you expected, possibly. But now let's consider mass. So the mass in the linear motion corresponds to what in the angular motion? So what is the concept of this quantity, first of all? Its name is inertia, rotational inertia, moment of inertia. But what is it equal to conceptually in the physical point of view? What is mass of an object? If you have an object, let's say a block on a frictionless surface, and you apply a certain force, and as a result, since there is no friction, you move it. You manage to move the object, of course. So according to Newton's second law, it gains an acceleration. So this force creates an acceleration for this block having mass m. But if, for example, the mass is twice the previous one, so let's say its mass is now 2m, and you apply the same force as before, so that the corresponding acceleration, instead of m, now we have 2m, and let's say this is a1, this is a2. So obviously, it was a1 is equal to f over m, and a2 is equal to f over 2m. In other words, as we see from this simple comparison, a2 is 1/2 a1. So a2, the acceleration of the second block, which has twice the mass of the first, is now 1/2 of the first block's acceleration. So now we can have a simple conclusion. As we increase the mass from some initial value to some greater values, for instance, if you do it as 3m, it will be 1/3. If you increase the mass of the object, so many kilograms, instead of 10 kilograms, this one has 20 kilograms. But the force remains the same. By the same force, you can create half of the acceleration to the block having twice the mass. So that mass is a way of, is a kind of difficulty for us. It is more difficult to move objects having greater mass by the same force. Of course, you shouldn't change the force, so force remains the same, and then we compare the different masses with the corresponding acceleration. So here, for instance, if your force is the same, the first object, which is lighter, which is half of the mass of the second, gains more acceleration. Alright, we know this already, but what about the rotating properties? Now maybe we can have different cylinders to rotate, discs. Now let's try to rotate different cylinders and compare the physical event. Let us rotate different cylinders. For example, it may be a very such as long one, such as a long cylinder, like a rod. This one, so it's a cylinder, but it's like a rod. Its length is much greater than its radius. So let's choose one such cylinder. For example, this may be the first cylinder, or the second one having lesser length but greater radius. For example, this one. Or in the third part, let's go to the other extreme. This time we have the widest radius, this. But let all of them have a mass of m. This one has a mass of m, let's say 10 kilograms. Each one is 10 kilograms. The same mass, but different radii. Here in this case, if you try to rotate it, so these are the axes of rotation. This has to be turned around this axis. This again has to be turned, let's use the upper parts, and this also is turned around the axis. So these dotted segments are the axes of the objects. So for example, we will rotate this cylinder along its own axis. To turn it around this axis is something else we will talk about. So there are two possibilities for this case. One is to turn it around the vertical axis, its own axis. So around its own axis like this. Second possibility is to turn it around this midpoint and through an axis or around an axis passing through the midpoint this way or the other way, which are the same. So we have two possibilities. One to rotate it around its own axis, the other is around this perpendicular axis. And we are talking about rotations around their own axis. But we have different disks, and we will try to turn them, not just pull by a horizontal force, and we don't want them to break from initial point I to final point F. They are turning in the same point around the fixed axis. Remember that we are still talking about rotation around the fixed axis. So this axis is not going anywhere. This object is just turning around this vertical axis or the other one or the other one. But do they show you the same difficulty? Is it still the same difficulty level of difficulty to turn each one of them? Of course not. First thing I will say is that. Just like these two different masses show you different difficulties to move along a single x-axis, these three objects, although they have the same mass, any one is heavier than the others. They have the same mass, and maybe they say 1 kilogram or 10 kilograms, whatever. But to turn these objects, these three objects having different radii, of course, are not the same. The level of difficulty is different. So one of them, let's say, has a radius r, for instance. This one, let's say, has a radius 2r. This one has 3r. Of course, this is a bit greater, but assume that they have different radii. Now, to turn the one with 3r is, of course, more difficult, harder than more difficult than to turn the one with R. So to turn the last one having radius 3r is of course more difficult, requires more torque, as we will see. We don't know torque yet, but as we will see. To turn the one with 3r, radius 3r, is of course more difficult than to turn the first one. What about the middle one? Of course it is again intermediate in difficulty, because it has intermediate radius. More than the first, less than the third. So the level of difficulty for the middle one is of course intermediate between these two. So we are interested in the first and third, if to compare. First one, the lengths, let me repeat, are not important. Of course the lengths are different, but this length is not important for rotations around the dotted axes of the cylinders, because each of them is a cylinder. But the last one is generally called a disk, because the, let's compare the first and third again. What is the name of this and the name of that? The first one, this one has a certain length, let's say L, and radius R. This one has a length, radius R. This one has a length and radius r. Okay? So in the first case we have L much greater than r. If you compare these two lengths, its length, just like this cardboard, its length is much greater than the radius, so that this is called a rod. In general, it is called a rod. And the last one, where its radius is much greater than the thickness L, is called a disk. So whenever we see, we read a problem talking about a disk, we understand that its radius is much greater than the thickness. And whenever the problem talks about a rod, maybe it's also in the electrical topics in physics 102, also we will have disks and rods, etc. Charged rod, charged disk. In this case, it is R much greater than L, but in this case L is much greater than R, and it is called a rod. Alright. And this one is a general cylinder. Its name is general. It is neither a rod nor a disk. Alright, now we are interested in the level of difficulty of rotating these things. So that level of difficulty, measure of difficulty, is called inertia. Eylemsizlik. So it is inertia, moment of inertia, rotational inertia. And it has a definition, of course. Let's first write that definition. The moment of inertia is first written by capital I. Rotational inertia, the rotational inertia I is defined as it is a summation. What kind of summation? For all I, it is mi Ri squared. So what is the meaning of this simple definition? For example, if it were only a point particle, if we just want to turn a point particle, let's say mi. Very, very little. Point particle means it has a mass, but it occupies a very little volume, just like a point. So the volume it occupies is very little, so we can take it as a point particle. But this one, for instance, is not a point particle for this reference frame. This can be considered as a point particle if you are turning this object by a rope having a radius of, let's say, 100 meters. From that distance of 100 meters, this object having a length of 50-60 centimeters can be taken as a point particle. But now in this room, this object is not a point, it has a certain size. This cannot be taken as a point particle. However, this ball, for instance, little ball, can be taken as a sort of point particle. So if you want to turn this object around an axis, okay? Let's say you want to turn this object, for example, maybe in a vertical circle or in a horizontal circle. So if you want to rotate this object, which is sufficiently little, it is of course not a point particle. In the atomic sense, for instance, this is a very large particle, very large object, macroscopic object. However, for some practical purposes, even such small balls can be taken as point particles. Because this radius, it has a radius of some maybe 1 or 2 centimeters. But if you turn this object at a radius of around, let's say, 40 centimeters, 1 centimeter is sufficiently smaller than 40 centimeters, so that in this rotation, for instance, you can consider the ball, this table tennis ball, as a point particle. You don't have much error in such approximations. If we just want to turn a point particle m1, mi. Here I, 1, 2, then this I is simply its mass times radius squared. But this radius is not the radius of the particle. It is the, for example, let's say this is a rod, and that thing, that small ball is attached to it. This distance is r, and this object has mass m. Just like this table tennis ball attached to the end of a rope, but that rope has a sufficient length compared with the radius of the small object. So if you want to turn this object in a certain horizontal circle, so we simply talk about a rotation. So for instance, let's say this thing is turning, it doesn't have to be horizontal, it can be vertical as well. Direction is not important in such calculations yet. Okay, this is the rotation. Angular speed is not important. It gives you a certain difficulty. So this rotation poses a certain level of difficulty to me. If it were heavier, for instance, if this ball were heavier, if it were made of iron, it would be more difficult for me to turn it in this radius. If I use a shorter radius, such as this one, it is easier, according to the expression. Shorter radius gives you less difficulty. If you increase the radius of rotation, not the radius of particle, let me repeat, because this is a point particle and we turn it in a circle of radius r. Now this is more difficult. If you still increase the radius of rotation, such as this one, it is more difficult than the first two. Of course, it is not easy to detect the change in the difficulty for such light objects, but if it were, let me repeat, if it were made of iron, lead, some material having greater density, of course it would be much more difficult. So for a point particle, this is the formula, m times r squared. So it has a unit, of course, inertia has a unit. What is the unit? Of course, we multiply kilogram from m, meter squared for the r, and therefore I doesn't have a shorter name. It is just, dimension of I is just kilogram meter squared in SI. Gram times centimeter square can be used maybe, but in SI this is the unit we use. Alright, this is a point particle. If, for example, we have more than one point particle turning around a certain axis, for example, let's say we have another ball, this one we have seen. If we have one more ball and attach it to another position along the road, so for instance, if I attach another ball midway, let's say, and try to turn the couple. For instance, this is the new object. It doesn't have to be horizontal. Let's say it's turning vertically as well. But we have two balls, 2 point particles having different distances from the axis of rotation. What happens to the total value of I? If we have more than one particle, if there are more than one particle in the system, if there are more than object. That object is a point particle, so very small one, whose size is negligible with respect to the length of the road from the axis. If there are more than one object in the system, in the rotating system, so I will be the sum of the two terms. M1 are 1 squared plus M2 are 2 squared. So that I is equal to now sum of I from 1 to 2 Ri squared. So in this case of two balls, one ball is here and one ball is there, and this system is turned around the vertical axis, for instance, and these are, let this distance be r, let this distance be also r, and we have identical objects having masses m and m. So that this I will be first object and its distance squared, mass m, distance is r squared. Next, so we have a summation. Second object, it has a mass m again, for example, identical mass. But this distance from the axis is now 2r, and we have to take it squared. R2 is 2r. So it will be m times r squared, 1 from the first, 4 from the second. So the total value will be 5 times mr squared. So the difficulty, level of difficulty has increased to a value of 5 mr squared in such a simple rotation. Again, let me repeat, there is no significance for the direction. It can be rotated, the system can be rotated around the vertical axis, around the horizontal axis, or around any axis at any angle. Angle is not important. Angular speed also is not important. We don't talk about omega yet. Now let's have another example to compare the inertias of the point particles, and then we could pass to the objects having a size. These objects do not have a size. These balls are taken as point particles. Now let me solve a simple example. Three small balls having masses 1m, 2m, and 3m are attached to a rope as shown. Rope of length L at equal intervals. As shown. So this is the first picture. Let's say the bigger object at the first 1/3, second object, and the lightest one here. So 1m, 2m, and 3m. And the distances are, let's say, L over 3. So this part is L over 3. This part is also L over 3. This part is again L over 3. Find the rotational inertia or moment of inertia. Find the moment of inertia I of this configuration. B, if m and 3m are exchanged, what will be the resulting moment of inertia? inertia I prime. Alright, we have three particles, 3 point masses, so we can apply the formula sum mi Ri squared. So in this first part, let's start by the definition. It is the summation I from 1 to 3 mi Ri squared. So begin from the beginning, nearest object. What is this mass? 3m. So will be 3m is the first mass multiplied by L over 3 squared. Plus, second object has a mass 2m multiplied by its distance from the axis, which is 2L over 3, but don't forget to square. And the last object is one single m multiplied by total L squared. Of course, the result will be in terms of ml squared multiplied by the remaining coefficients. So from the first we have 1 over 9 times 3 is 3 over 9, 1/3. From the second object, second term, we have 4 over 3, 4 over 9, 8 over 9. So let's not write it as 3 over 9, 3 over 9. This is 8 over 9. This is 1, 9 over 9. Okay, let's check it. 1 over 9, 3 over 9 from the first, 4 over 9, 8 over 9 from the second, and full object 9 over 9. So this result will be 20 over 9. So I will be 20 over 9, whatever it is, 20 over 9 m times L squared, the first moment of inertia. Now in part B, we replace the heaviest one with the lightest one, and they are interchanged. So this new combination is the following. Along the row we have the least one, again the intermediate one, but the greatest one comes to the outermost position. So we expect the inertia to increase somewhat. But let's see the ratio now. In this case, this is 1m, that is 2m, this is the 3m. So let's apply the terms. The formula to the term. First one is, let's find it here, I prime. First term, first mass is m. What is that distance? L over 3. M times L over 3 squared. Intermediate one is again there in the same place. So its mass is 2m, its distance is 2L over 3, but don't forget to square. 2L over 3 squared. But the last one, heaviest mass, 3m, is at the distance of full m, total L, from the beginning, from the axis. So it is L squared. Now we expect it again, m times L squared multiplied by 1 over 9 from the first. So after having a comparison for the point particles, now let's consider objects having a size, such as a disk, a sphere, spherical shell, rod, for example. And we generally have, in Physics 101, we consider the spherically symmetric or let's say cylindrically symmetric objects. So we don't have, for example, we don't have a square type of plate. In Physics 101, we will not be dealing with the squares or rectangles or cubic objects. Of course, we do those in the classical mechanics courses in the physics departments, but in Physics 101 we are limited with the either the sphere, solid filled sphere or spherical shell, which is empty like a ball, or a disk or a rod, cylindrical objects. So now let's consider the objects having a size. So unlike these point particles, now we will consider the full disk, total sphere. Consider a certain ring, for instance. Just a ring. For example, this is a ring. It is empty. But it has a certain mass, certain radius. If you turn this object, for example, around this axis, what is the inertia for this object? Or it can be a solid disk. a kind of cylinder. For an object having a size, which means it's not a point particle, such as this ring, for this ring. Let me do it a ring first. So the mass is just in the ring, so it is empty. A ring. Mass m, radius is r. So if you choose, what is the definition of I? It was a summation, remember, mi times distance ri squared. But the distance for each mass element, for example, if you focus on such a mass element here, let me call it mi, m1. This is m1, that is m2, m3, m4, m1 million. If you divide this ring into 1 million small pieces, each mass has the same value if you equally divide them, and each mass is at the same radius r from the center O, so that each ri of the radius is just r. So we can take this constant outside. Therefore, I turns out to be, let me take r squared and sum of the masses, I from 1 to n. But this sum is just the total mass of the particle. Therefore, it is, for this ring, it is I is equal to mass times r squared. For the disk, similarly, you can consider such an addition, but disks are objects having, for the particles having different radii. So this, for example, this is a disk. It's a solid object. If you look at it from above, this is the top view. So this distance radius is r. Its mass is, let's say, m. But this radius is that one. This is the top view. If you look down from above onto a disk, you see the circular top surface. And that surface, for example, if you consider a certain mass element, this mass element, it is at a distance r, the distance r, its mass is very little dm. So we cannot find it by just simple summation, because although masses can be taken as identical, distances are different. However, in the first case of ring, we get the same fixed radius r, so it is quite easy to take the result. But now, this summation should turn into an integration. And of course, I can show you how we find this simple result of 1/2 mr squared by integral, but we generally leave the integrals outside of the scope of Physics 101, so that you will be interested in such integrations, especially in Physics 102 or the classical mechanics courses in physics departments. So I will immediately write the result. So the inertia for a disk, let me write it on the board. This is not a ring, but a disk. It's a full object, solid surface object. So it is just 1/2 total mass, total radius squared. So for a disk, it is 1/2 mr squared, and it is easily obtained by some simple integration. But let's leave it aside. So a disk is a kind of cylinder, as I said before. It's a longer cylinder. Longer cylinder is not called a disk. It can be a rod or another cylinder. For example, this is a disk, but this is a cylinder. This is called a disk. This is called a cylinder. It has mass m. It has mass m. It has radius r. It has radius r. In those cases, the inertia for the cylinder is also 1/2 mr squared. So the inertias are 1/2 m times r squared and 1/2 m times r squared. But be careful for the axis of rotation. We talk about the axis of the object. So the objects are turned around. Objects are turned around the axes of the objects. And let me repeat, this is a kind of cylinder, and we talk about the rotation around this axis, but rotation along a perpendicular axis is something else, and it will be taken into the topics only when you talk about the rod. Rod is an object having a length much greater than the radius. So let's also consider another important thing, which is the sphere. Maybe a solid sphere, maybe a spherical shell. Solid sphere or spherical shell. Spherical shell is like a ball, basketball. It's empty inside. It has only a cover. But solid sphere is like an iron ball, for instance. So it is an object and it is filled inside. Filled. And the characteristics, the properties are mass m, radius r. Always you will have mass m, radius r of the particle. But spherical shell is an object like a basketball or tennis ball or any other ball which is empty inside. So it has a mass m and radius r. But the mass is only on the surface. Again, these are calculated, the inertia values are calculated by integrals, of course, but those integrals are a bit beyond the scope of Physics 101, so let me write the results immediately. So solid sphere is I is equal to 2 over 5 mr squared, solid sphere, but spherical shell is 2/3 mr squared. Which one do you think is easier to rotate, to turn around? Maybe at first sight you may say that since it is empty inside, this is easier. At first sight one may say that it is easier to turn this object around its axis rather than turning the solid object, solid sphere, around its own axis. However, if you compare the results, it seems that the inertia for the empty object, the ball, is greater than the solid object, 2/3, 2/5. Do we make a mistake? No. The critical point is here. We assume each of them having the same mass m. Same mass. For example, if this object, let's say this object has a mass of 1 kilogram. Let's say this object has 1 kilogram. This object also has mass 1 kilogram. Radii are the same. Let's say, for instance, radius is 0.1 meter, radius is 0.1 meter. However, as we see from the calculated results, it is easier to turn this first object than the second, because remember that, always that, the greater the inertia value, the more difficult it is to turn it around that axis, just like the mass. The greater the mass, the harder it is to pull it or to push it. But in the rotational topics, it is the following idea. The greater the inertia, rotational inertia, the greater the moment of inertia, also called moment of inertia. Rotational or moment of inertia. The greater the rotational inertia, the harder it is to rotate. Not to pull, but rotate. So if you compare them, we understand that I for the spherical shell, so I for the spherical shell is greater than I for the solid sphere. How come? It is because of the assumption of the same mass. This object has the mass 1 kilogram, but it is distributed over the volume. However, here, all the mass, total mass of 1 kilogram is just squeezed, concentrated in a small region, and that small region is as far away from the axis as possible, which is the radius. So as we have seen from the previous examples, we attached 3 balls along the rope, and the greatest inertia was obtained for the case where greatest, heaviest objects are attached at the end of the rope, or as far away from the axis as possible. So in this case, all the masses taken, distributed in a small volume, just the thickness of this shell, spherical shell, just like an onion, for instance, shell of the onion. This is the shell which contains the mass, and all the mass m, whatever it is, the same mass as the solid object, is now distributed only a much smaller volume, so that of course it is more difficult to rotate. But in other words, if you take just this shell from the first object, of course it is much easier. Without the mass inside, of course it is a very light object, very little process, very easy process. If you take just the shell and take out the inside, of course it is much easier. But this is not that thing. In this case, we have the same mass at 1 kilogram, 10 kilograms, whatever, but the same mass is distributed over the much smaller volume, so that this is more difficult to rotate. Alright, now let's go to the do some other things. For a cylinder in general, and for a disc or cylinder, what is a disc? It is such a shape. What's a cylinder in general? It is such a shape, whose R is and length L, R is like L. So radius and length are comparable. One is not maybe 10 times the other. They are maybe 2 times, 3 times, 1.4, whatever. So our radius and length are comparable generally for a cylinder. But if one is much greater, it is either called a disc or a rod. Remember, we have said that. So for a disc or cylinder, the rotational axes are the axis of rotation. The axis of rotation is what? Let's say this is the disc, and this is the axis of rotation. And along this axis of rotation, we said that I is equal to 1/2 mass times radius squared. So this is the radius r, and that is the mass of the object. For example, if m is equal to 200 grams and r is equal to 50 centimeters, what is the inertia? Let's say put the numerical data in, 1/2 m. What is m? Of course we don't use 200, we write 0.2 kilograms multiplied by radius, but we don't write 50, we write 0.5 meters. 0.5 meters squared. This is just 1/2, it will be 1/4, 1/2, 1/5, 1/4. So 1/40. So I is equal to 1/40. It is 0.025 kilogram meter squared. Numerically, we can find the values like this. But don't forget to convert the kilograms to kilograms, centimeters to meters if they are given in the other ways. Alright, so this is the axis of rotation. However, as we have seen previously, if you make this cylinder as long as possible, so it is like like this case, for instance. This is called a rod. It is, of course, in general, it's a cylinder. However, We don't call it a cylinder, we call it a rod. And in rods, we have other axes of rotation to take into account, because in this case, since it is a very small radius, these inertias are neglected. We don't take into account this kind of rotations for the rods. For a rod of any material, for a rod, so for example, this is the rod. Let me draw it horizontally. And this axis of rotation, if you want to turn it like this, we take I simply 0. We assume there is no difficulty. It is, well, anyone can do it easily, is the assumption. Anyone can rotate this thin rod whose length is much greater than its radius r. Okay, so this is the radius r, but that's the length L, and L is much greater than r. For such a rod, we take the inertia values as 0. However, it has a kind of moment of inertia. That one is for a different axis of rotation. That axis is the perpendicular axis. So if you rotate this object around this perpendicular axis, which passes through the midpoint, so if you want to rotate it like this, so around the midpoint it can be turned. And now it has a certain inertia. Or this is another possibility. The axis, maybe the z-axis, it can be turned like this, or the x-axis, for example, but not the y-axis. So this is negligible, but the others are important, as we will see in the problems. Now, what is that value of I? Here, the axis of rotation is perpendicular to the object. The important axis, important means non-zero inertia. The axis for which the inertia is not zero, I is not zero, is perpendicular. Is the perpendicular axis to the rod. So for example, this is the rod, and it can be turned around this midpoint. The axis, let's say this is the so that this axis can be turned, let's say, up and down like this, through the midpoint O. Of course, not through the midpoint, you can choose any other point, as we will see in the parallel axis theorem, but now, for simplicity, let's assume it is turned around the axis which passes through the midpoint of the rod. And what is that value? Of course, this is also calculated by integral. This I is also calculated by some integral. Not mi, but dm. So let's, for instance, this is the case. Let me just write the integral and then get the result. For example, this is x equals 0. And if you choose any value, dm, little mass element dm, so that this distance from the axis direct is x, for example. So it is x squared dm, and x, now in an integral, when you learn how to take the integrals, you put the, for the definite integrals, you put the limits, lower and upper limit. So from x equals 0 to x equals half of the length. So this corresponds to x equals L over 2. This corresponds to x equals minus L over 2. So from 0 to L over 2, and you multiply by 2, because also there's the same part to the left part, the left end of the origin O. X squared dm, if you simply take it, let me just result immediately. And maybe dm can be written as physics 101, students are not responsible for those integrals, let me repeat. But let me show how you get this relatively simple case. dm is just linear mass density times the distance dx. What does it mean? We take a very short distance dx along the x-axis. This is the x-axis. What do we mean? So this is the rod, and this midpoint is taken as 0. And we are interested here. So for example, when you consider some part here, that small thickness is dx. There is a certain mass, very little m, just contained in this short interval. That one is dm, differential, d comes from differential, dm. So if you add up, but this is at a distance x, this is like a point particle, the small table tennis ball. So there are several balls attached one after the other along this rod, as we assume. So that it is just the integral. We have a 2 here, integral x squared. What is dm? dm is lambda dx, lambda times dx. So it will be twice x. Remember that? Maybe you remember from previous other courses. So x to n dx turns out to be x to the n plus 1 over n plus 1. So we have x to 2. It will be 2 plus 3 cubed divided by 2 plus 3. X to the 2 plus 1, it will be 3. It will be divided by 2 plus 1, multiplied by lambda, and limits are from 0 to L over 2. Next it will be 2/3, 2 over 3. I will be 2 over 3. We have a lambda here. Lambda is the general ratio, density. Total mass by total length. Total mass and total length L. At the end I will substitute m over L. So lambda is just total mass by total length, m over L. So lambda remains now. It will be x cubed. X to the 3. And between 0 to L over 2. We have 2/3, lambda is m over L, x cubed. You first put the upper limit, L over 2, to the third part, minus lower limit 0 to third power. So this is nothing. We have 2/3 m over L, L cubed over 8. 2 becomes 8, L becomes L cubed. So there are cancellations. This L makes it square. And this makes it 4, so that I turns out to be, for a rod, 1 over 12 m times L squared. So this is the expression for the rotational inertia of a rod. But don't forget, only for this kind of rotations around the axis passing through the midpoint. And let me repeat again, Physics 101 students are not responsible for getting these integrals. You will anyway be in the exams, for instance, you will be given this these inertia values immediately. The important thing for a 101 student is to be able to apply these equations to the problems as required. So that's the important point right now for the 101. So this is the inertia for rotations around those axes. However, for this kind of axis, this will be I is equal to 0. Now let's consider another important point. Because so far, we talked about turning around the midpoint, around the center. So far, we talked about turning around the center of mass. Remember the abbreviation CM. center of mass. If the, for example, for this object, if it were a spherical shell or a full sphere or a disk, we talk about this kind of rotation around the center of mass. So the object was turning around the midpoint. Midpoint is center. The circular objects, whether it's a disk or a sphere or a spherical shell, is turning around the center of mass. What if it doesn't turn around the midpoint but somewhere else? Now we will see that important section. What is I? If it turns around a different point. Now, for example, do we get the same difficulty in turning an object at a different point? Maybe for the spheres and disks, it is not very easy to detect, to sense those changes in the difficulty. But for a rod, it is more easily observable. For instance, let's say we have a rod of some more than 2 meters. This is a kind of rod that we have already talked about. And we have said that the inertia, rotational inertia of turning the object around the midpoint, axis passing by the midpoint, let's say this way, this is a kind of rotation around this axis. This is an axis perpendicular to the axis of the object, rod. This is 1/12 ml squared, we have seen. One more thing is, the other identical kind of rotation is this rotation. Okay? So these are more difficult, but to turn it this way is almost nothing. We have said that it is 0 for a rod. Now let's try to rotate it around a different point, not the center of mass, but let's say 1/4 from one end, 3/4 from there. So this is, as you can easily detect, is more difficult for the person to turn it. If you go further and further to one end, the right one or left one doesn't matter. If you go to further away positions and try to turn it like this, it is even more difficult. If you try to turn it from one end, so full rod is in front of you, and you are trying to rotate this object around an axis passing through the one end. So as you can easily obtain, detect, it is the hardest way of rotating it. The right hand end is no different, but the easiest one is the center of mass. If you try to rotate it through the center of mass, it is the easiest possibility. Alright, now let's compare the kinds of rotation and get the new formula for a rotation around a different point. This is called parallel axis theorem. It is called parallel axis theorem. What does it mean? If you don't rotate the object through the midpoint, through the center of mass, but through some other point, around the point which is somewhere other than the center of mass. So parallel axis. This is the axis, this is the parallel axis. New one. Let's try to get this equation and then apply it to some given problems. Assume that we have an object of any shape. Let's, for simplicity, let it be a disk, for instance. Let's say this is the disk. It doesn't have to be, by the way. The equation is not limited only to some symmetrical objects or objects having simple geometries. This is a valid expression that I will try to derive. So that's the x-axis, y-axis, and this is the center of mass. All right, what was the expression? Remember, the expression for I, rotational inertia, was a summation. I from 1 to n. I means m1, m2, m3, m1000, m1 million, whatever. If you divide this object into 1 million pieces, very small pieces, each one has a name m1, m2, m132, whatever. So that each object, mi, assume it is here, for instance, should be multiplied by its distance from the origin, Ri squared. So Ri squared. But now, this is what we call mi. And of course, that mi is a characteristic mass element. It can be anywhere else on this disk. It doesn't have to be a disk, but for simplicity, we take it like a disk. Okay? Now assume that we don't want to turn this object, because we know what the result is. I, center of mass, is just 1/2 m times r squared. This is something already written. For the full disk, having mass and radius r, but if it is turned around the center of mass, it shows you this much difficulty, this much rotational inertia. But now we don't want to rotate it around the center of mass, but somewhere else. For example, let's say this point or that point. So for example, this is the point where we have to rotate. Let me call it point P. We want to rotate it. We want to rotate it, rotate the disk. It doesn't have to be, but let's choose it as disk. We want to rotate the disk around point P. Around point P. What are the coordinates? They are important, of course. These coordinates are, let me say, this is A and this is B from the origin. The coordinates are this point P. Coordinates of point P are A along the x-axis, B along the y-axis. Of course, they don't have to be positive either, but for simplicity, let's choose the first quadrant for the mi and p, so we can see the distances maybe more easily. We want to rotate the disk around point P instead of origin O. Okay, because origin O is already the center of mass of this object. If you want to turn around P, then this distance is important. So this distance is important for mi. For any other point, so that distance, the other distance. So this is our new origin. Our new point of rotation is point P. So this equation will take a new form. Then I will be inertia, rotational inertia will be written as so it is the summation of mi and ri minus, so be along the x and y directions. So it will be mi times, so that for all I 1 to n, mi times xi minus a squared plus yi minus b squared. So these small distances, maybe large but small, let's say these distances are added. So for example, this part is xi minus a, and that part is yi minus b, because the positions of this point is xi, yi. And then these differences will be squared and added up. So this is the new form for each mi. So what is the next step? So we have mi. If you write them separately, first term, this is, remember, like, what is that expression? Let me write it here. A minus b, or for example, p minus q squared. What is that? P squared minus 2pq plus q squared, as you remember. So this is the difference squared. So it will be written, both of them will be written in this form. Square of the first minus 2 times the two terms plus square of the last. Okay, so mi times xi squared, first term, minus again mi times twice first term xi, second term a, plus summation mi a squared. We continue with the second block, plus summation mi yi squared, minus again, twice again, minus mi twice yib plus summation mi b squared. So we have 6 such terms, 2 of which will be 0. For example, if you consider these two, what are they? If you add them up, anyway, this is an addition. If you write it in a new way, summation mi xi squared plus yi squared, first double. Next, second part, let's say this part, summation mi a squared plus b squared, and then we have 2 more terms. But those 2 terms are simply 0 and 0 because of the definition of the center of mass. Because these are just 0 and 0. Sum over mi xi is 0 for the center of mass. Because if, for example, let me consider just a simple case, very, very simple case. If we have only 2 objects, to show why these are 0. If you have only 2 objects, let's say one is here, the other is there. But let's say this is 1 unit, this is 2 units. But this is 1 m, this is 2 m, but this is 1 m. So with respect to the origin, this has a contribution of 2 m, this is a contribution of minus 2 m, so they cancel. If you look at these summations, it is always a cancellation. So mi may be this point or that any other points. If you this one has a corresponding mi symmetrically opposite part with respect to the origin. This mi has also a similar symmetric point, etc. So they cancel. Similarly in the y regions also. So these terms are 0, and we arrive at that final result. So this expression, some of them is just the I center of mass. And this one is the distance of a squared plus b squared is that distance. Therefore, we arrive at the expression I is equal to I center of mass plus m times h squared. What is that h? H is the distance of the new point with respect to the origin, or with respect to the previous center of mass. So this is the new equation. Let me write it in a better way. The new value of the inertia, rotational inertia, is the inertia around the center of mass plus, necessarily plus, never a subtraction but an addition necessarily, plus some new term. What is that new term? It is the total mass of the object, the disk for its total mass, times square of this distance between the center of mass and the new point, where h is the distance between the where h is the distance between the center of mass and the new point. Between the new point, let's say P, in the example I have written, between the new point P and the center of mass. So let's apply it to the case of rod, for instance. Let me write it in this example. Because remember that I have tried to rotate this long rod, wooden rod, and observed a gradually increasing level of difficulty as I move to one side, one end of the rod, from the midpoint, from the center. And we will now apply this expression to the rotation of a rod. For a rod of mass m, length L, find the moments of inertia around the axis passing through points A and B. Let me draw the full rod, and this is the center of mass of the rod. And A, let's say, is this point, B is that point. Of course, they could be on the other side of the rod as well, no difference. But this total length is L, but the first part, let's say this is L over 4, this is also L over 4, so these are L over 4, L over 4. You divide it into 4 identical pieces, L over 4 each. Okay. So I around point A. Let's apply this equation directly. Because anyway, Physics 101 students are not responsible for the how the integrations are obtained, how these formulas are obtained. This equation I just tried to show you, but you can apply it directly to the given problems without any, even in the final exam, you are not responsible for taking those integrals or showing how this result is obtained, etc. Okay, I sub A. If you want to rotate it around this quarter, what do we mean by that? This is the full object, that's the midpoint, and this is point A. So that this will be the fixed point, this will be the fixed point, and the rod is turned around point A. What is that A? It is 1/4 from one end. So apply this equation directly. What is the I center of mass? If you rotate it around the center of mass, it was already found as 1 over 12 m times L squared. Now we have to add something because it becomes more difficult in this new rotation. Plus total mass, which is m. H, what is H in this case? H, remember, is the distance between the new point, that is A, and the center of mass. So this distance is our H in this equation. So that it is H, instead of H, I write L over 4. L over 4, but don't forget to take the square. So IA will be what? m times L squared multiplied by 1/12 from the first term, 1/16 from the second term. So that it is 28/12 times 16 ml squared. So if you cancel by 4, so this will be 3, that will be 7/48. So that I will be 7/48, almost 1/7. So that I will be, I means I sub A, because if you rotate it around the point A, it is this much. Around B, it is something else. 7/48. 7/48 mass times L squared. So this is the new moment of inertia, almost 1/7. 7/49 will be 1/7. What about the end, which is more important in more widespread in the problems? I around B. Now again we have I center of mass, or I0 in some books. I center of mass is sometimes written as I0, plus m times h, but there's a new h now, because in this case we are turning the object like this. So this is the fixed point, and this is the fixed point B, and this is the free rotation. Therefore, what is the new distance for h? This is the distance new h, which is just L/2. New point is B. Center of mass is here. What is this new distance for h? It is just half of the length. So we have to add, in addition to 1/12 ml squared, we have to add m times L/2 squared. So that IB turns out to be 1/3 ml squared. As you see, it is 4 times more difficult. If you compare, for instance, IB over I center of mass is 1/3 ml squared, 1/12 ml squared. So after the cancellations, IB is 4 times I center of mass. As I tried to rotate the long rod, wooden rod a minute ago, it was more difficult to rotate it around one of the ends. Of course it is more difficult. It is 4 times more difficult, as you see from the simple application. 4 times more difficult. Instead of 1/12, we have now 1/3, which is 4 times more difficult. Of course, it is the same difficulty if you turn it around the other end. No difference. If you turn it around the other end, there is no difference. Instead of A, if you choose A here, A prime, it is the same difficulty. So one side or the other side make no difference. Now let's consider the rotational kinetic energy. After having seen the parallel axis theorem also, let's see the new idea, kinetic energy. We have seen kinetic energy, but now we have the rotational objects. Now we have the rotational kinetic energy. Because we have already seen in the linear motion, we know that if we have an object, a block for instance, this object, let's say, has a mass m, is moving at a velocity v0. Of course it has an energy, because some work has to be done to stop it. If some work is required to stop an object, necessarily it has some kind of energy, and here of course it has an energy, kinetic energy, in this reference frame, because in this frame, this object has a velocity. So V0 is defined for a frame, for a reference frame, coordinate system, like this room for instance. In front of us, something is moving. That object has a certain velocity and it has a certain mass m. So that this object has a kinetic energy, which is 1/2 m times V0 squared. We know this and we have solved several problems on this idea and the energy conservation. Now, instead of a moving object, we have something which is rotating. For example, let's go back to the previous wheel. This object, let's say, is turning. It is not going anywhere. It doesn't have a kind of kinetic energy like 1/2 mv squared. Yeah, it has a mass m. Sure, if you weigh it by some scale, you get the mass of the object. All right, it has a mass. It has a velocity. Yeah, it has a velocity, but angular velocity. How can you get the energy, rotational kinetic energy of this rotating object? Which V should we use? Is it the velocity of this point which is very near the origin axis, or it is something intermediate, or it is just on the surface, on the circumference of this red dot? Do we mean which velocity should we choose as our velocity V? So we have to find a new formula for this kind of energy, rotational kinetic energy. First of all, let's remember the previous lecture. Let's have a certain correspondence between the velocities. First, let me draw a circle. Let's say this is a disk, for instance. Let's say it's a disk. Okay? So let's choose a certain radius. Any radius and anywhere. Okay? Let's compare only 2 points. In the previous lecture, I have chosen 3 points, A, B, C, etc. 1/3, 2/3 full radius. But let's just compare 2 points. One is on the circumference, the other is halfway along the radius. Let me call them A and B. A and B. So this object is turning well by some omega, and what we also have seen the vector nature of the angular velocity. If this object is turning like this, remember that this is the vector, omega vector, that represents the direction. So this is the vector towards you, because this object is turning in this counterclockwise sense. So by using the right-hand rule, we understand that the direction represented by omega is out of the board. But if it were rotating in the clockwise sense, then we would choose it, again by the right-hand rule, into the board. So this much we have already seen. If that is the direction of rotation omega, alright, then omega for point A, omega for point B, they are the same, as I said previously. If this circle, this completes one full turn, point A makes a full turn, point B makes a full turn, and the angles they sweep are equal, 360 degrees, 2 pi radians for A, 2 pi radians for B, 2 pi radians for any other point. So omega A, omega B, omega C, they have the same omega. However, if you compare the linear velocities, let me use the vectors, say this one is V sub A, that one is. Now let us apply the idea of parallel axis theorem to a certain example. For example, let's say we have a combination of rods, like a letter H or letter I, whichever you like. So this object can be turned around different axes. One possibility is to turn it around this red one, like this. Red one is staying in the same position, but the others are turning. This is a possibility. Another possibility is to keep black one or blue one at rest, but the rest is turning around it in such a circular manner. Another possibility is maybe these ends, lower ends may remain the same, but the thing can rotate as a whole, like this, all together. Maybe there are other possibilities. For instance, this is also a possibility. The midpoint of the red remains the same, but the system may turn around this position like this. These are all a few of the possible cases. So let's find the total inertia, in other words, total degree of difficulty in these kinds of rotations for different axes of rotation. Three identical rods, each of mass and length L, are connected to form a letter H, as I have shown you. Find the rotational inertia I around A, B, C, and D. So this is the shape. Let's say around the axis AA prime, around the axis, let's say AA prime is a possibility, or BB prime, or CC prime, or DD prime. BB prime, for instance, may be this axis. This is BB prime. Or CC prime, C prime, and finally let's choose a DD prime. For instance, this is DD prime, D and D prime. So let's try to calculate just using the parallel axis theorem. Part A. AA prime. For instance, let me also keep the configuration with us. So this is the object. AA prime. So red pen remains the same, but it is turned like this. So let's give names to these rods. First one, middle one, and last one. The vertical ones are 1 and 3, horizontal ones, let's say 2. So in each case, let's say AA prime, of course I1 plus I2 plus I3. All three will be added. But in some calculations, some terms will be 0, or will be taken to be 0, and some of them will have more than the center of mass value, because of the parallel axis theorem. So for instance, in this case, we have, in this rotation, let me always keep the figure with us. So in this rotation around A prime, number 1 is just turning around this midpoint. So it only has, I1 is only 1 over 12 m times L squared. Similarly, third one, black one, is also making a turn around the midpoint. So the third one is also 1 over 12 m times L squared. But the horizontal one, middle one, is just turning like this. As I said before, there is no contribution. It can be taken as 0. So that IA prime is just 2 over 12. 2 over 12 m times L squared. Or 1 over 6, but let's keep 2 over 12. Case B. Now we have BB prime. What is BB prime? it is an axis passing vertically through the midpoint of the middle rod. So that BB prime rotation is the following. For instance, this BB prime is midpoint of the red object remains the same. So it will be such a rotation. So in this case, all three will have contributions. Number one, I BB prime. Number one is totally turning around the axis at a distance of L over 2. Total, there is no 1 over 12 ml square anymore. Full object having mass m is turning around a certain radius. So first one will be m times L over 2 squared. Similarly, third one does the same. It is also turning total mass around an L over 2. But middle one is just turning around its midpoint. So middle one is 1 over 12 m times L squared. Third one is similar to the first, m times L over 2 squared. So it will be ml squared multiplied by 1 over 4 plus 1 over 12, 1 over 4. 3 over 12, 7 over 12. So it is 7 over IBB prime, 7 over 12. Right? 3 over 12, 6 over 12, 7 over 12, m times L squared. So this is the new value for the BB prime axis. Part C. Part C, around CC prime. What is CC prime? It is this axis. So CC prime axis, in this case, we keep these tips, upper tips of the two pens, and the whole thing is turning as a whole like this. So each of these objects will have a contribution. So I CC prime. First one, number one. Number one is turning around its end point. And as we have seen previously, if the rod is turned around its end point, it is 1 over 3. Not 1 over 12, but 1 over 3. So the first object will have a contribution 1 over 3 m times L squared. Middle one is turning together at a distance L over 2, full mass L over 2 squared, and the third one is also turning around the end point, so of course this is also 1 over 3 ml squared. So that ICC prime will be ml squared multiplied by 1/3 plus 1/4 plus 1/3 again. 11 over 12. So that ICC prime is 11 over 12 m times L squared. And finally, we will find BD prime. BD prime is the axis which passes through the left object. For instance, here we have this one is remaining, but the right hand part is turning as a whole like this. So this is the kind of rotation. Again, from the first one we have no contribution. So I do IDD prime. IDD prime is I1, which is nothing, plus the middle one, but turning around the end, 1/3 ml squared, and the last one is totally turning, total mass is turning around the radius L. So m times L squared. So I dd prime will be ml squared 1/3 plus 1. 4 over 3. So that I dd prime is 4/3 m times L squared. Now we can make comparison between the four cases. Which one is greatest? Let's first of all equate the other terms. For instance, if you make that, it is 16 over 12. 4/3, 16/12 ml squared. So each one has been 12 as the denominator. So greatest one, if we arrange them in increasing order, what is the least one? 2/12, IA prime. Let's also keep these axes on the board. The smallest one is IAA prime. Increasing order. Next one is BB prime. Next one is 11 CC prime. And the greatest one is DD prime. So this is the order of, this is the increasing order. What do we mean physically? The greatest one, the smallest one. DD prime. What is DD prime? It is this combination. You keep one rod as stationary and turn the rest around it. This is the most difficult one. You don't have to think about the horizontal, you can also think vertically. Maybe this is the same kind of rotation. One rod remains the same, the others are turning around it. But vertical, horizontally, we don't consider G, for instance, mg, etc. mg type of things, forces, do not enter in such calculations. This is the inertia, the level of difficulty in turning that system. We are not interested in the gravitational effects, etc. So IDD prime is great. What is the easiest one? IAA prime. So the easiest one way of turning the object is around the middle one. So this is the easiest one, and that's the hardest one. This is the hardest one. Keep one of them the same. But if you keep one stationary, but turn the rest around it, this is the hardest one. The others are intermediate. BB prime, for instance. BB prime, this kind of rotation is intermediate. CC prime also. CC prime was this kind of rotation, is also neither the greatest nor the smallest. But the greatest and smallest ones are these, and let me write a sentence for this as a comment. Comment. The greatest inertia corresponds to hardest to turn. The smallest I, easiest to turn. Don't forget, please, this kind of conclusions. The greatest I value in a system, for example, corresponds to the hardest way of turning it, the greatest difficulty shown against you. And the smallest one, such as here IAA prime, for instance, corresponds to the easiest way of turning it. Although the sum of the masses do not change, the sum is the same. For example, if you take this object, let me take it again. If I take this object, put it on a certain surface, okay? I put it on a surface, for instance, then, for example, we put it on a surface. This object is put on a maybe frictionless or some friction, doesn't matter. If I try to pull this way or that way, the other way, you have the same difficulty. We don't turn it right now. This object, if you attach a rope to any part of the object and try to pull it on a certain surface, maybe with some friction, you have the same difficulty. You have to apply the same minimum force to move this object to get rid of the friction, static friction, for instance.
it doesn't matter on which point you have to attach the rope. But once you talk about turning the object, then which axis do you choose? The axis having the least I inertia corresponds to the easiest way of turning that object, or the one having the greatest value of I corresponds to the most difficult axis of turning it. Now let's talk about the energies and solve some problems using the energy, rotational energy and energy conservation. For instance, when we have a ball, for instance, this ball is a spherical object. This is a spherical object. If it is turning in the same place, like this, if it is turning around in the same position, it only has rotational kinetic energy, which is 1/2 I omega squared. But it also, if it is moving, as we will see in the next chapter, rolling motion, it will also have some linear kinetic energy and also some rotational kinetic energy. But they are corresponding terms, and the velocity can be found as according to V is equal to omega times R, for instance. V and omega can be converted to each other. V and omega, angular and linear speeds, can be converted as V is equal to omega times radius. So let's consider, for instance, about an example. Let's say, first let me draw a picture and then write the text. So this is the, for example, disk. And around it some rope is wound, and then we will have a block. Then this block is released, so it is falling down. Later on, and let's say here, on the one hand, the object is falling down. On the other hand, of course, the disk is turning. Now let me write the problem. An object of mass m is attached to the end of a rope passing over a disk of mass m, radius r. Rope has negligible mass. End of a mass. Let me write a massless rope. Massless rope. Massless rope means the mass of the rope joining disk and the object has a very little mass, so it is negligible with respect to the other masses. An object of mass m, this object, is attached to the end of a massless rope passing over a disk of mass capital M, radius capital R. Then it is released. Find A the linear velocity of the object, the linear velocity V of the object after having fallen at this height h, after having fallen a height h, and b, the angular velocity omega of the disk at that moment. The angular velocity omega at that moment. So as you see from the picture, of course the problem gives you just the first one. The rest is some explanation. The problem from the book, for instance, gives you only the first picture, not the others. So it gives you that there's a disk and some rod passing over it attached to the block at the end. Initial position. The rest is up to you. You should understand that once it is released, the object will be falling down while turning the disk in the same position. The disk is not going anywhere, but the disk will have some angular speed omega, and that's some rotational kinetic energy, 1/2 I omega squared. Of course, the problem should give you the inertia for the disk. You don't have to memorize. I is equal to 1/2 m times r squared for the inertia of the disk. The other object has some linear kinetic energy, and also because of a falling motion, its potential energy will change. And since there is no external force acting on the system, or they cancel any net external force, the energy is conserved. First thing is that energy is energy, but which kind of energy? Potential and kinetic. But kinetic is also two kinds, linear and angular. Since there is no net, F external, we have F external is equal to there is not external, but there is no net non-conservative force such as friction, such as friction. The energy is conserved. The energy is conserved. So let's compare two instances. One here and two there. The block is just near the disk, and the block has fallen a distance of h from the initial position. So we compare these two instances. Therefore, energy, mechanical energy 1 is just mechanical energy 2. So the mechanical energies are the same. Then, for example, we compare, let me draw the picture again. This is the beginning and that's the end. If it is end. It is not the end because it is just falling with a certain velocity, unknown velocity, so it doesn't stop here, it will continue. But we are interested in these cases. Point 1, point 2, or height h is the amount that the block falls down. And these energies should be equal. For simplicity, we can choose this level to be 0 level. You can choose this one also, but doesn't matter. For simplicity, this one can be taken as 0 vertical, 0 reference. So initially, what is energy? E1. E1 is just, since it is at rest, the block doesn't have a velocity, disk is at rest, we have chosen this level to be 0 level, so there is no initial energy. It is simply, of course, E1, remember, potential 1 plus kinetic 1. There is neither a potential nor a kinetic energy. So it is initially 0 and 0. But here, what is E2? E2 is potential plus kinetic. There are both of them. Potential, what is the potential energy when the object reaches here? With respect to the zero reference, it has fallen down to a negative value of minus h. Therefore, it is m times little m. Please don't confuse the masses. Capital M is the mass of the disk, which doesn't move anywhere. Little m is the mass of the block, which falls down. Little m, g, and minus h. But plus kinetic energy. There are two kinetic energies, one for the block, one for the disk. There are two of them, and they are, one is 1/2 little m v squared, which we don't know, v, plus the other one has only rotational kinetic energy, 1/2 I omega squared. First thing we have to write is this. Since there is zero on the other side, we can take negative term to the other side. So we have 1/2 m times v squared plus 1/2 I times omega squared. Take it to the other side, mgh. So this is the first thing. Next we continue. Now we have to find the relationship between V and omega. So V and omega. If, for example, R is the radius, and this object, for example, this point of the row has the velocity V, this point has the same velocity V, this point has the same velocity V. So whatever the velocity the block has, little v, is the same velocity at this point of the row. So that this circumferential point on the disk has the velocity v, and that v can be written in terms of omega and r. So that this v or this omega can be written as v over r. So instead of this omega, we will write v over r and squared. So this is the conversion. And reducing two unknowns to only one unknown, v. Because the problem says find first v and then omega. Then we have a very simple equation, 1/2 little m v squared plus 1/2, and then inertia, which is 1/2 mr squared, 1/2 capital M capital R squared is the I value, inertia value, and then omega squared. But we don't write omega, we write v over r. So we have v over r squared. On the right we have m times g times h. So there's only, it seems, one cancellation, which is the cancellation of these. So we have 1/2 mv squared, 1/2 little m v squared, 1/4 capital M v squared is mgh, so that v squared turns out to be m over 2 plus m over. Now let's have one more energy conservation problem. So we have a rod of mass m, length L, so L is the total length, and for example these are the points, and let me call this midpoint C. So this is just L over 2, of course this is also L over 2. A uniform rod of mass and length L. Like that is initially stationary in a horizontal position, like L. is initially stationary. Stationary means at rest. In a horizontal position. Then it starts to turn around the left hand A. Then it starts to turn around the left hand and point A in a vertical plane. A in a vertical plane. Now find A, its angular velocity omega, as it passes by the vertical position, B, it's the linear velocity of point B, the linear velocity VB of point B at that instant, and C, the linear velocity VC of its midpoint. The linear velocity V sub C of point C, its midpoint, at that instant. At that instant means as it passes by the vertical position. Now we again have obviously a conservation of energy problem. So if we set any position as our zero position, such as this one for instance, can be chosen as zero level at the beginning. We can maybe add one more part to this. Let's add, before starting to solve, let's add one more part, C, D. If a little ball was attached, for instance, if a little ball of mass m, little m, were attached to point B initially, what would omega be? So let's complete it to a fourth part. So part A, we have, as I said, conservation of energy. But the first level now is just a single rod. Little object is added in the last part. So this object starts to, maybe let's take this rod for instance. This is the rod, point A, point B, and midpoint C in this picture. So it just falls down. That's all. As simple as that. It just falls down, and when it passes by the vertical position, what about the omega, angular velocity just at this moment, and the linear velocities of point B and point C. In the last part, we will add, for instance, this little ball here, and then together it will rotate. Alright, so from the energy conservation again, what is the reason for energy conservation? There is no friction, first of all. No friction. Just because of gravity, it just falls down. From energy conservation, from the energy conservation. E1 is equal to E2. What is 1? What is 2? 1 is the initial configuration. 2 is the vertical final configuration. And anyway, of course, if the problem asks to find the omega, v, etc., somewhere in between, also we can find those values too. Because 0.3, for instance, maybe the rod is not vertically down, but let's say the rod is initially like this, maybe here. While the angle with the horizon is theta, we can also find the omega of this rod, but it is geometrically, it requires some other calculations. The easiest one is, of course, to compare the horizontal one with the vertical and moving one. So let us write the energy conservation. E1. What is E1? Initially, it has no speed. And it has no potential as according to our choice of 0. So initially, E1, which is U1 plus K1, and it is 0 and 0. E2. E2 corresponds to U2 plus K2. Is there any U2? Yes, sure. What is the height fallen by the center of mass, not the tip? You should consider the length. The center of mass falls. The center of mass is, let's say, this piece of object, this point here. And as this rod turns by a 90-degree angle, pi over 4, pi over 2, as it turns by 90 degrees, and the tip arrives at minus mgl, but the midpoint just falls half of it. And we are interested in the motion of the center of mass. The center of mass of the rod falls a height of half of the length, L over 2. So that U2 is, when it comes here, center of mass was here, center of mass comes here. So what is that distance? It is just L over 2. So, but negative, of course. Potential is now minus m times g times L over 2. What about the kinetic energy? Do we have anything like 1 over mv squared? 1 over 2 mv squared? No. We have rotational kinetic energy. 1/2 I omega squared. What is I? We have a rod. But the rod is not turning around the midpoint, it is turning around the tip. One end. So we have seen previously how the I, rotational inertia, becomes when this object is turning around the end point. Not 1 over 12, but 1/3 ml squared. So that it will be plus 1/2 I omega squared. Potential plus, what is I? I is 1/3 m times L squared, and omega is the unknown, the only unknown. So that 0 for the initial total mechanical kinetic energy is now minus mgl over 2. Minus mgl over 2. It is the potential energy change for the center of mass. Plus 1/2 I, which is 1/3 ml squared times the unknown omega squared. So it is easy to find omega. Take it to the other side. 1/2 1/3 ml squared omega squared. Take it to the other side. M times gl. So m's cancel. Sorry, there's also a 2, and these 2's will cancel, so that one of the l's also will cancel. This l cancels one of them. So omega squared is just 3g over l. There's g remaining, 3 remaining, and 1l, so that it is 3g over l. Therefore, omega, which is valid for all the points of the rod, is root 3g over l. There is no need to write a unit radian per second, for instance, because it's a parametric problem, as I said before several times. There is no need to write a unit here. You can leave it as your result can be left like this. Part B, it is the velocity of the end point, VB. VB is, of course, omega times full length L from V is equal to omega times R. What is the radius of point B with respect to the origin? It is full total length L, so omega times L. Therefore, VB is simply root 3G over L multiplied by L. Let's put this L squared inside. So VB is just square root of 3G and take it as L squared. So these L's will cancel. VB is simply root 3G and L. So this is the linear velocity of the endpoint B. Next part is the velocity of the midpoint C. So V sub C is just again omega times, what is the radius of midpoint? It is L over 2. So here we have to write L over 2 for the midpoint. Of course, it has half of the linear speed as the linear speed of endpoint B. So we have VC will be L over 2 times omega root 3G over L. Again, we have L squared inside. So VC is 1/2 root 3GL. So as I can easily see, VC is 1/2 VB, of course. So this is the comparison of the midpoint's velocity with the end's velocity. In part D, we added one more object. So this was the case. Now that's, let's say, object point mass M. Mass M is the, capital M is the rod. So when it falls down together with this object, so that, what about the energy? Energy conservation. Now we should take into account this little m as well, both in the inertia and in the velocity terms. How can we find the new energy equation? Again, E1 is equal to E2. 1 is the initial configuration, 2 is the vertical, so final in this interval. Alright. Again, we have chosen this level to be 0 level. So initially, E1, E1 which is U1 plus K1, it is 0 plus 0. There is no energy at the beginning coming from the potential or kinetic terms. But, what about the final case? E2. E2 is U2 plus K2. What is U2? Let me write it separately. U2. This potential energy, as it passes by the vertical position, consists of two parts. One, that as I have written before, the center of mass falls a distance of L over 2. But also, this object, which has a mass, falls a distance of L. So there are two terms. One is negative capital M, G, and L over 2, because it falls a distance of half of the length. And the other one is also minus little m, this small object, falls a height of L, minus mg and full L for the potential energy change. What about the kinetic energy? The kinetic energy also has two contributions, two parts. One is 1/2 I omega squared. The other is 1/2 mv squared. Because this one now has a certain velocity v, which is the velocity of the end point of the rod. So again, we can write K2. This K2 has 1/2. I is 1/3 ml squared. Omega is, write it as omega squared, but plus 1/2 little m. What is V? V is equal to omega times L. So we have here, instead of V, we have omega times L squared. So because we are after omega, we want to find the angular speed omega. So after some arrangements, we have, let's take these negative terms to the other side as positive terms. Let me take L squared outside, common term. L squared over 2. L squared over 2 is the common term. Inside we have m over 3, capital M, over 3 from the first term. Let me also take omega squared outside. So let's go slowly. We have 1/2, 1/3 m L squared omega squared plus 1/2 m omega squared L squared equals these two terms positively on the other side. Capital M GL over 2, little m GL. So we can now rearrange in an easy way. So 1/2 is common, so take 1/2 outside. L squared also common, omega squared is also common. Inside we have remaining terms, m over 3, capital M over 3 from the first, so we finished first term, plus little m only because the others are already written. On the other side we have GL, common terms, multiplied by capital M over 2 plus just little m. So we can arrange these. This becomes capital M plus 3 little m over 3. This becomes capital M plus 2m over 2. Now what do we get further? We can cancel one of these L's also, and we want to find omega squared, omega, so that omega squared over 2 times L multiplied by m plus 3m over 3. On the other side we have only G multiplied by m plus 2m over 2. So it is easy to find omega. Let me write the result here. Is there any other cancellation? No. Maybe these twos will cancel, that's all. So that omega is, the first line, omega squared, alright? Omega squared is G over L, and 3 also, 3G over L, multiplied by m plus 2m over m plus 3m. And there is no other term missing. Omega squared is L comes here, 3G over L and the rest. So omega is simply 3G over L multiplied by m plus 2m divided by m plus 3m. Now let's make a comment immediately to compare the results with or without little object. And then stop. So after this comparison, we will see that. Let's write it as a comment. In the previous case, there was no little m. In the previous parts, there was no little object. M. So if you set m equals 0, little m equals 0, if we set now m is equal to 0, we should get the previous result for omega. Do we? Yes, we do. We should, if we set now m equals 0, we should get the previous omega. What was it? Remember, omega was root 3 times GL. No, G over L. 3 times, yeah. 3 times G over L was the previous omega. If you multiply by L, we will get, for the linear velocities, root 3GL. But for omega, it was root 3G over L. Now, if you set this m, that m 0, because if you don't put any little object, there's no little m. And you should just, you are left with just a single rod. And you should find, from this result, you should find, it should reduce to the previous omega, which was root 3G over L. If it reduces, it is alright. If it doesn't, then it means we make a mistake. But we didn't make a mistake because these m's, if they are set to 0, and these then will cancel, capital M's will then cancel. So we remain, we get the previous result of, so omega is now root 3G over L multiplied by m over m, plus 0 plus 0. So that these m's now cancel and we get the previous result, so it means we made it correctly. Alright, we solved some examples today considering the parallel axis, first the rotational inertia, then the parallel axis theorem, and then rotational kinetic energy. Next time we will have some other applications, and we will see some new concepts such as the torque, which corresponds to force in linear motion. And then also we will solve maybe the same example or some other examples using the torque concept. Because some problems can be solved by energy conservation, just as we did here, also by torques. Which one is easier can be used. But some other problems, for instance, will be solved when we see the rolling motion. Because rolling means, as I said before, this is the ball. If it is just turning in the same place, then it is, if it is just turning in the same place, such as this one, it is pure rotation. But if it is also moving along a line, it is it will be called rolling. For instance, this object, if it is turning in the same around the fixed single axis, it is pure rotation. But if you ride it on this bicycle and move also, it will have two parts. One is pure rotation, then linear motion of the center of mass, so that together it will be called rolling motion, rolling with friction, without friction, let's say, without slipping. The rolling without slipping will be also an important part of the of this chapter. But now, for now, this much we have seen.